Alright, so this question is from May June 2016, paper 23, question number 4. ठीक है जी. So in this question, it is saying that acetoin and diacetyl are two of the compounds, right? So we have acetoin and diacetyl. They are two compounds that give butter its characteristic flavor. Their skeletal formulas are shown. So basically we have two compounds, acetoin and diacetyl, and these two compounds they are present in butter and their skeletal formulas are shown. Alright, now the first part is give the systematic name for acetoin. So we have to name acetoin. Now अगर आप ये structure देखें acetoin का, we have two functional groups present in acetoin. One is ketone and the other one is alcohol, right? So in acetoin there are two functional groups. Number one is ketone and number two is alcohol. So that means it is a multifunctional group, and if we have more than one functional groups present in an organic compound, then we have to decide the priority order. So you just have to remember this thing, that if we have two functional groups, like here we have ketone and alcohol, then the functional group which has carbon present in it, and that one is ketone. So ketone has this carbon present in it. Ketone, the functional group of ketone is C double bond O. So the functional group which has carbon present in it would be the primary functional group. So we will start numbering from where ketone will get the small number. Alright, so ketone will get the priority, and we will start numbering from where ketone will get the small number. So this would be carbon number 1, carbon number 2, carbon number 3 and carbon number 4. So we have total 4 carbon atoms present in our chain. Alright, and we have a hydroxy group. When OH comes as branch, then we call it hydroxy. So we have a hydroxy group present at carbon number 3. So the name of this compound would be 3-hydroxy butane, because 4 carbon atoms are present. So butane, and for ketone the suffix is -one, and we have to write the position of ketone as well. So ketone is at carbon number 2, so butane 2-one, right? So this would be the name of this compound, 3-hydroxy butane 2-one, or you can write it like this as well, that 3-hydroxy 2-butanone. But mostly in marking schemes you will get answers in this form. So it is better to write the position of the functional group with the suffix, like here. Alright, now the next part is identify the reagents and conditions necessary for the conversion of acetoin into diacetyl. So now we have to convert acetoin into diacetyl, and first let me just erase all this data. Alright, so now we have to convert acetoin into diacetyl, and for that conversion they are asking about the reagent and conditions, that what conditions and what reagents will be used. So if you look at acetoin and diacetyl, if you look at their structures, one of the functional group, there is everything similar in these two structures. Like we have this ketone group present on carbon number 2, a ketone group present on carbon number 2. The only difference is that at carbon number 3 we have an OH group present in acetoin, and we have a ketonic group present in diacetyl. So that means alcohol has been converted into ketone, and this is oxidation. When we convert an alcohol, and which alcohol converts into ketone? Secondary alcohol. So this is a secondary alcohol because this is attached, the carbon which is attached directly to OH group is attached to 2 carbon atoms, 1 and 2. So that means this is a secondary alcohol. So whenever a secondary alcohol oxidizes, it converts into ketone. So this is oxidation. So for the oxidation of alcohols, we need acidified potassium dichromate, and conditions would be heat under reflux. Alright, so you just have to remember this thing, that primary alcohols oxidizes into aldehyde if the conditions are heat and distill. Secondary alcohols oxidize into ketone, and primary alcohol oxidize into carboxylic acid if the conditions are heat and reflux. Alright, so the next question is the IR spectrum for acetoin is shown. So this is the IR spectrum for acetoin, and the question is explain the main features of this spectrum with reference to the peaks with wave numbers greater than 1500 per centimeter. Okay, so this is the characteristic IR absorption frequencies for some selected bonds, right? Basically this is taken from the data booklet. So now we have 4 columns in this table. First column represent the bonds, second column represent the functional groups containing the bonds, and the third column is absorption range in wave numbers, and the fourth column is appearance of the peak. Now before discussing this table, let me just explain this graph. Basically this graph has 2 axes. On y-axis we have transmittance, and x-axis is wave numbers, which is measured in per centimeters. So the major purpose of IR spectrum is to identify the functional groups present in an organic compound. Alright, why we are doing IR spectroscopy? To determine the functional group present. Alright, to identify the functional group present in an organic compound. And how IR spectroscopy serve this purpose? Basically जब आप किसी भी organic compound पे IR radiations strike करते हैं तो होता क्या है कि जो आपके bonds हैं, let me just add a new page here to explain this IR spectroscopy. So what happens is that let's suppose we have a carbon-hydrogen bond. Let's say we have a carbon-hydrogen bond, and this carbon-hydrogen bond, it behaves like a spring, right? So this behaves like a spring, and when IR radiation hits this bond, let's suppose these are IR radiations. So when these IR radiations hit the bond will absorb some amount of energy. Alright, it absorbs some amount of energy and starts vibrating. So it needs a specific amount of energy for vibration. It will absorb that amount of energy, and rest of the energy would be transmitted. So this is transmitted light, which we are observing in the graph, right? This is the transmittance. So let's just say if all of the energy is transmitted, then we would get a straight line at 100. That means this is 100% transmittance. But this is not happening in the case of this particular compound, because there are certain we can say inverted peaks for transmittance. That means the transmittance has been lowered down. So if transmittance is lowered down, that means this is absorbance. This is the amount of energy which is being absorbed by the compound or by the bond for the vibration. So you just have to remember this thing. When any particular bond absorbs some IR radiation, it starts vibrating. It behaves like a spring, it starts vibrating, and every bond requires different amount of energy for that vibration. And हमने क्या करना है, हमने simple functional group identify करना है. So we just want to find out what amount of energy is being absorbed by that particular bond, and then we can simply identify that which particular bond is this. So if you just look at this data, so we have different bonds present in this table. For example, the first one is carbon oxygen bond. Now, carbon-oxygen bond is present in different functional groups. For example, it is present in alcohols, it is present in ethers, and it is present in esters. So just by finding out that a particular compound contains CO group or CO bond, it doesn't mean you have identified the specific functional group, because CO bond is present in 3 different types of functional groups or homologous series. Alright, so we need additional informations as well, but let's just talk about CO bond. So CO bond is present in 3 different types. That means if you have identified that a particular compound contains CO bond, that means you have narrowed down your search and you know this thing that now this compound is only it's either belong to alcohol or ether or esters. Now the next thing is absorption range. Now absorption range is measured in wave number. And what is wave number? It is basically reciprocal of or inverse of wavelength. So wave number is inverse of wavelength. Alright, so if the unit of wavelength is centimeter, the unit of wave number would be per centimeter. So wave number can be defined as it is the number of waves passing per centimeter. This would be the definition of wave number. So we are measuring the wave numbers of the absorption ranges. So for carbon-oxygen bond, the wave number absorption range is 1040 to 1300, 1040 to 1300, and the appearance of the peak is strong. S is for strong and W is for weak. And a strong peak means a very high absorption or a very low transmittance. A strong peak means it has a low transmittance. Alright, so it has a low transmittance. So on x-axis we have wave numbers, and just remember one more thing. Basically we divide this graph of IR spectroscopy in 2 parts: above 1500 and below 1500. So below 1500, this is called fingerprint region. Below 1500 is known as fingerprint region, and above 1500 this is called functional group region. Alright, so fingerprint region, it is different for every compound, every single compound. For example, if we have 10 alcohols, each alcohol would have different fingerprint region. It is just like the fingerprints of human beings, that is different for every other human being, right? So fingerprint region is different for every organic compound. So every alcohol, every alkene, every carboxylic acid would have its own fingerprint region. A very few similarities would be present in the compounds of same homologous series in the fingerprint region. But the functional group region would be same for all the compounds belongs to a particular homologous series. For example, the functional group region would be same for a homologous series. So all the alcohols would have same functional group region. All the alkenes would have same functional group region, right? So normally we just talk about functional group region, and this is why you can see in this question, with reference to the peaks with wave numbers greater than 1500. So they're only talking about the peaks or the absorptions above 1500, not below 1500, because these are very difficult to identify. And if you look at the absorption range of CO bond, it lies in the fingerprint region, right? So इसका मतलब ये हो गया कि the absorption for CO bond, it would be very difficult to identify, right? And normally we do not talk about this absorption. All the other, if you just notice all the other absorption ranges, are above 1500. Only CO absorption range is below 1500, and all the others are above 1500. Okay, so now I hope all have I hope all of you have understand what IR spectrum is. Now let's just focus on the question. So the question is, explain the main features of this spectrum with reference to the peaks with wave numbers greater than 1500, right? And this is the IR spectrum for acetoin. And just remember the structure of acetoin. In acetoin we have a C double bond O group and an OH group, right? So now the peaks above 1500, we can call them peaks or we can call them absorption, right? So this is one absorption, and the other absorption is right here, and the third absorption is right here. So these are three absorptions which are present above 1500. Now one more thing you have to understand is that most of the students, because in the graph in this table we have ranges for absorptions, right? Like for example, for carbon oxygen double bond, there are different because if a compound has carbon oxygen double bond, that means it could be an amide, it could be a ketone and aldehyde, or a carboxylic acid, or an ester. So if it is a ketone and aldehyde, that means the absorption range is 1670 to 1740. Now most of the students, they think this thing, that the absorption range is the width of this peak. Just notice this thing, that it has nothing, the absorption range has nothing to do with the width of the peak. बेसिकली एब्जॉर्प्शन आपने जो देखनी है, आपने सिंपल ये देखना है, द लोएस्ट पॉइंट ऑफ द पीक, द लोएस्ट पॉइंट ऑफ द पीक, दैट वुड give you the absorption. So for example, for this peak, this is the lowest point, right? So we just notice the lowest point, this is 1500, 1600, and then 17. So this is around 1720. So let's say this peak is at 1720. Then for the other peak, the lowest point is this. For the other peak, the lowest point is this. So this is around 2900, and then for the next peak it is 3000, 3100, 3200, 3300, 34. So this is around 3450. All right, so ये चीज़ सिंपल ध्यान में रखें, that you have to notice, you have to note the lowest point on the peak, the lowest point on the peak, right? So this would give you the idea which functional group is present. So basically the ranges which are present, why they have given us the ranges in periodic in this IR spectrum table, the reason is that every, like let's suppose if we have an alcohol, let's say if I have this alcohol, right, and the alcohol has its particular range above 3000, right, and in this compound not only alcohol is present, we have a Br group also present in this compound. So Br would affect the IR absorption of OH. Due to the presence of Br, OH will absorb, let's say this is one alcohol and the other alcohol is propanol. So both these alcohols have OH group present, both these alcohols have 3 carbon atoms present, but one of them has a Br group present to the next carbon which has OH group attached on it, and the next structure, let's suppose if this is A and this is B, so A is different from B in terms of that it has a Br group attached and B has no Br group attached to it. So there would be a slight difference in the IR absorption of this OH and this OH. So this is why they have given us ranges, because every alcohol would have a different kind of environment, and that environment would affect the amount of radiation it will absorb for vibrations. Alright, so this is why they have given us these ranges. So these ranges have nothing to do with the absorption peaks width. Okay, so we have 3 peaks present in our compound. The first peak is at 1720, and obviously that would be due to ketone and aldehyde, because in acetoin we have ketone group present. So the range is 1640 to 1740, and our absorption lies within this range. So that means this is for C double bond O. So we can simply say the first point would be the absorption at 1720 is due to carbon oxygen bond. Alright, so this is one main feature of this structure, or you can also mention here that this is ketone group. Alright, the next peak is at around 2900, and at 2900 that means this would be an alkene. CH bond has a peak at 2850 to 2950, a strong peak. Again, this is a strong peak, right? So the peak at 2950 is due to carbon hydrogen bond. So that means this peak would be present in every organic compound, because every organic compound has carbon hydrogen bond except for very few. Now the last one is 3450. So 3450 would be obviously due to OH group, and this is an alcohol, so that means it would be 3200 to 3600, right? And this is an alcohol, so our peak also lies within the region. So this is at the peak at 3450 is due to OH bond. Alright, so I hope you all now understand this thing, that how to explain the features of an IR spectrum. And just remember this thing, never give the ranges in your answer. Never give the ranges in your answer. Give that value where the peak touches the x-axis. Alright, so you only have to mention the lowest point of the peak where it touches the x-axis. So I hope all of you have understand how to explain the main features of an IR spectrum, what is an IR spectrum, and what can we find out through an IR spectrum graph. Alright. Now the next question is, state and explain how the IR spectrum of diacetyl would differ from the IR spectrum for acetoin. So the difference between the IR spectrum of diacetyl and the IR spectrum of acetoin. So if we look at the structures of these two compounds, so in acetoin we have a ketonic group and an alcohol group, but in diacetyl we have only two ketone groups. So that means there will be no absorption at 3450 in case of diacetyl, because it has no OH group. Okay, so the difference in the IR spectrum of diacetyl and the IR spectrum of acetoin is that, as in diacetyl there are no OH bonds, therefore no absorption at 3450. Alright, so this is another question on infrared spectroscopy. So basically this question is from October-November 2018, paper 21, question number 4. The structure of glycolic acid is shown. So this is glycolic acid, right? This has the COOH group and OH group present. Okay, so complete the table to show what you would observe when an aqueous solution of glycolic acid is added separately to each of the reagents. So they have given us some reagents here: sodium carbonate, 2,4-dinitrophenylhydrazine, commonly known as DNPH, and acidified potassium dichromate or acidified dichromate ions. So complete the table to show what you would observe when an aqueous solution of glycolic acid is added separately to each of the reagents. So when we add glycolic acid in aqueous solution of sodium carbonate, what would we observe? We have to write the observation here. If a reaction occurs, state the functional group of glycolic acid that is responsible for the reaction. So obviously if we observe something, that means reaction is happening. So if reaction is happening, if we write some observation in the first column, then we have to tell them that whether the reaction is happening or not and which functional group is responsible for that reaction, because we have in total two functional groups present here, a carboxylic acid and a hydroxy group. So sodium carbonate, it reacts with acids. All right, you know this thing that metals react with acids, acids can react with metals, acids can react with metal oxides or hydroxides, and acids can react with metal carbonates, right? So they can react with metal carbonates. OH group, on the other hand, it cannot react with metal carbonates, although it is very slightly acidic, but it cannot react with metal carbonates. It can only react with strong metals or active metals. All right, so sodium carbonate will only react with carboxylic acid. It will only react with carboxylic acid. And when a metal reacts, or when an acid reacts with metal carbonate, what would we get? Whenever an acid reacts with metal carbonate, we get salt, water, and carbon dioxide. So when acids react with metal carbonate, we get salt, water, and carbon dioxide. So if carbon dioxide produces, that means what would be the observation? Fizzing or bubbling, you can say, right? So does a reaction occur? Yes, the reaction would occur. And the functional group which is responsible for this reaction is COOH, or you can write carboxylic acid. Okay, so the next question is 2,4-DNPH. So 2,4-DNPH, this is a confirmatory test for, or reagent for, carbonyl compounds, for aldehydes and ketones. But here in the glycolic acid, neither we have an aldehyde nor a ketone, so that means 2,4-DNPH will not react with glycolic acid. So we can say there will be no visible observation or no reaction. So does a reaction occurs? No. And functional group, obviously nothing required here. Then acidified dichromatine. Now dichromatine, this is an oxidizing agent. This is an oxidizing agent, and this will oxidize the alcohol or OH part. Acids cannot be oxidized by dichromatine. So acidified potassium dichromate will oxidize alcohol, and the observation we get is acidified potassium dichromate is of orange color, and when it oxidizes a substance, the color changes from orange to green due to the change in oxidation state of chromium ion. So the color changes from orange to green. So the reaction occurs, yes, and the functional group responsible is OH group. So very simple question. Now the next part is two reaction sequences to make glycolic acid are shown. So we are making glycolic acid, and they have given us two reaction sequence. This is sequence A and this is sequence B. Draw the structure of X. We have to draw the structure of X. Now let's look at this reaction 1, how X is being forming. So we have HCHO, that means this is an aldehyde with one carbon atom, H, C double bond OH. This is methanol. All right, all those organic compounds which have this OH group present, C double bond OH group present, these are aldehydes. So this aldehyde is reacting with hydrogen cyanide and sodium cyanide. So this is a typical reaction of carbonyl compounds. Nucleophilic addition. You can react any aldehyde or ketone with HCN in the presence of sodium cyanide for nucleophilic addition, because this has this carbon oxygen double bond. So when this HCN reacts with methanol in the presence of sodium cyanide, the CN group will be attached to the carbon of the carbonyl group, which is partial positive, and oxygen is partial negative. So the CN group is added to carbon and H is added to oxygen. So the structure, we have to draw the structure here. So the structure would be HCH. and the double bond between carbon and oxygen would be broken, and oxygen would have now a hydrogen attached to it, and the carbon would have cyanide group, C triple bond N. So this would be the structure of X. Name the reagent for reaction 2. For reaction 2. Okay, so in reaction 2, X is being converted into glycolic acid. Alright, so if you just look at this reaction, what have we done? That everything is similar except for this cyanide group. Instead of cyanide group, this glycolic acid has a carbon with 2 hydrogens, so this is CH2, and then this has OH group, this is OH group, and instead of cyanidine, now this has COOH group, right? So the cyanide group is being replaced by COOH group, so this is the hydrolysis of nitriles. And for hydrolysis, this is acidic hydrolysis. So for acidic hydrolysis, we need an acid, right? So the reagent for hydrolysis of cyanide would be hydrochloric acid or phosphoric acid or sulfuric acid. So this would be hydrochloric acid, or you can write sulfuric acid, and you can also write plus water as well, because this is hydrolysis, right? So just remember this thing, that whenever a cyanide is being converted into acidic group, that means it is acidic hydrolysis of the nitrile. Next part is name the mechanism of reaction 3. Reaction 3. Now this is reaction 3. So in reaction 3, what is happening? Ethanoic acid is being converted into bromoethanoic acid. So if you look at this reaction, what have changed in this reaction is that we have the CH3 group on the reactant side, and on the product side now we have CH2 and a Br. So that means one of the hydrogen from CH3 is being replaced by Br. So that means this is the reactions of alkane in which the halogen group replaced the hydrogen. So the mechanism of reaction 3, this is free radical mechanism, the reaction of alkanes. CH3, from CH3 group, one of the hydrogen is replaced, and instead of that, in the place of that hydrogen, now we have a Br group present. So this is free radical substitution. Free radical substitution. Suggest the essential condition for reaction 3. So for free radical substitution, we need ultraviolet radiations to break the halogen bond so that free radicals can be generated. So this is ultraviolet radiation. Okay, so the next part is reaction 4 occurs via an SN2 mechanism. All right, so this is reaction 4. Reaction 4. In reaction 4, you can see that Br is being replaced by OH. So this is nucleophilic substitution reaction. So they're saying that this occurs via an SN2 mechanism. Primary alkyl halides, they react through SN2 mechanism. So as we have this, the carbon which is attached to bromine is directly attached to only one carbon. So that means it is a primary alkyl halide. Alright, so they're saying that this react through SN2 mechanism. Complete the diagram for the mechanism of reaction 4. Include all relevant charges, partial charges, curly arrows, and lone pairs. So we have to draw the mechanism here. And the attacking nucleophile is OH group. OH is the attacking nucleophile. It attacks on partial positive carbon. So first we apply the charges on carbon and bromine. So carbon is partial positive and Br is partial negative. Oxygen has a lone pair available, the OH minus. Right, so this is the attacking nucleophile. So it would attack on the partial positive carbon. So let's say this would attack on partial positive carbon. So the electrons would move on this carbon, and the electron between carbon and bromine, because carbon is already making 4 bonds. This carbon is already making 4 bonds, 1, 2, 3, and 4. So this is already making 4 bonds, and now OH is transferring its electron density to this carbon because it is partial positively charged. So as soon as OH ion will start transferring its electron density towards carbon, carbon will break one of its bond, and carbon halogen bond is most likely to break because Br is a highly electronegative atom. It is a good leaving group, so it would take the electron density towards itself. So as OH minus, it starts transferring its electron density towards carbon. The electrons between carbon and Br would start transferring towards the Br group. So the arrow, one of the arrows would be drawn from OH towards the partial positive carbon, and the other arrow would be from the center of the bond between CBr towards Br. Alright, so these two electrons which are shared between carbon and bromine, they would be transferred towards Br. So the result would be OH ion at the end. Now we have OH ion attached with the carbon, and Br would be removed as Br minus. So this is the mechanism, the SN2 mechanism. In SN2 mechanism, both bond breaking and bond making occurs in a single step. So you can see that at one side, OH ion is transferring its electron density towards carbon. So this bond is in the making process. This is bond making. And on the other side, CBr bond has been breaking. So this is bond breaking. So in SN2 mechanism, both breaking and making occurs in a single step. Both bond breaking and making occurs in a single step. Alright, so this is the mechanism for the reaction. Next part is glycolic acid can also be made by reacting glyoxylic acid with NaBH4. So this is glyoxylic acid, and they're saying that glyoxylic acid can be converted into glycolic acid when we react glyoxylic acid with NaBH4. State the role of NaBH4 in this reaction. So NaBH4, I hope everyone knows this thing, that NaBH4 is a reducing agent. And in this reaction, you can see that the ketone or aldehyde, the aldehydic group C double bond OH, this is being reduced into alcohol. So aldehyde has been reduced into alcohol. So that means it is a reducing, NaBH4 is acting as a reducing agent. Now the next part is write an equation for this reaction using molecular formula. Use atomic hydrogen to represent NaBH4. So in organic reactions, mostly oxidation and reduction, we write the equations in terms of atomic oxygen or atomic hydrogen. So here we also have to write the equation in atomic hydrogen form. So first let's just write the molecular formula of glyoxylic acid. So we have 2 carbon C2, 2 hydrogen H2, and 1 2 3, so 3 oxygen O3. And if we write the molecular formula of glycolic acid, in glycolic acid we have 2 carbon C2, 1 2 3 4, 4 hydrogen H4, and oxygens are still 2. So that means 2 hydrogens are being added, and this is what reduction is, gain of hydrogen. So now we have to decide where these 2 hydrogens have been added in the structure. So if you look at the bond between carbon oxygen, this is a double bond, right? So this double bond would be converted into a single bond, and both carbon and oxygen would gain 1 hydrogen each. So this would become C2H4O2. Double bond will be converted into single bond, and both carbon and hydrogen will gain 1 hydrogen. So that means we are adding 2 hydrogens, 2 atomic hydrogens. So this is the equation in terms of molecular formula. Okay, now next part is the IR spectroscopy, infrared spectroscopy. When glycolic acid is heated in the presence of, sulfuric acid catalyst, a new compound YC4H4O4 is formed. The equation for the reaction is given. So 2 molecules of glycolic acid react in the presence of sulfuric acid. So, and we get this new compound, and in addition we get water molecules as well. So 2 glycolic acids are reacting with each other in the presence of concentrated sulfuric acid, which is being acted as a catalyst, and we are getting molecule Y and water. The infrared spectrum of Y is shown. This is the infrared spectrum of Y. On y-axis we have transmittance, on x-axis we have wave numbers. State how this spectrum differs from the infrared spectrum of glycolic acid. Explain your answer with a particular reference to the peaks within the range 1500 to 4000 centimeter. Alright, so we have to remain in this range 1500 to 4000, and in this range we have to explain that how this is spectrum. Now this is the spectrum of the compound Y. When glycolic acid when two molecules of glycolic acid reacts in the presence of concentrated sulfuric acid, we get this compound Y, and this is the IR spectrum of Y. And they're saying how this spectrum differs from an IR spectrum of glycolic acid. So let's just first draw glycolic acid here. We have CH2 OH, C double bond O, OH. So first of all, glycolic acid would have a peak of carbonyl group, and the peak of carbonyl group would be at around, if you look at the ranges, so the carbonyl group of carboxylic acid, this is around at 1680 to 1730, and we have 1500, 1600, 7. So we have a peak here which is around in the same range, so that means this is not a difference. And then we have peak for OH group of carboxylic acid. So for glycolic acid, there must be an OH peak of the carboxylic acid which would be in the range of 2500 to 3000, and there is no such peak because if you look at the table, this must be broad peak, strong and very broad, and we do not have any broad peak. Broad peaks are like these kind of peaks are broad peaks, so there is no broad peak. We have a peak here at around 2900, this is due to CH, and there is no broad peak due to the OH group of carboxylic acid. So we can say that the first difference between the IR spectrum of glycolic acid and Y is that it does not have an absorption at 2500 to 3000 due to RCO2H, right? And the next peak would be due to this alcoholic OH, the OH group of alcohol. So the OH group of alcohol, this is from 3200 to 3600, the hydrogen bonded alcohol. So this peak would be in this range 3200. The OH of alcohol, its range is 2500 to 3000, and the OH of carboxylic acid, its range is 2500 to 3000, and the OH of alcohol, its range is 3200 to 3600. So we do not have any peak in this region. This is 3200 to 3600, so there is no such peak. So we can also say that this is one difference, and the other difference is Y does not have an absorption at 3200 to 3600 due to ROH. All right. So in terms of the peaks, we have determined what would be the difference between the IR spectra of Y and glycolic acid. Now, suggest a structure for Y. Now, this is interesting. Two molecules of glycolic acid are reacting with each other, and we have only one peak. If you look at this IR spectrum, we have only one peak at around 1600, right? So this peak suggests that this is a carbonyl group. So we have a carbonyl peak here, and two molecules of glycolic acids are reacting with each other. So let's just first draw the two molecules of glycolic acid. So let's suppose this is C double bond O, CH2 OH, OH. So this is one molecule of glycolic acid, and the other molecule of glycolic acid, let's just draw it in another color. So the other molecule of glycolic acid would be C double bond O, OH, CH2, OH. So these are two molecules of glycolic acid, and if you look at these two structures, they both have carboxylic acid and OH group present, and we know this thing that carboxylic acids and alcohols react in the presence of concentrated sulfuric acid to give ester. So this would be an ester formation, right? And in ester formation, what would happen is that the OH group would lost its hydrogen, and the carboxylic group would lost OH. So one water molecule would be removed from this side. So H would be lost from alcohol, and OH would be lost from carboxylic acid. So one H2O is formed. They have already told us this thing that two water molecules are being forming. So one H2O is formed, and the other H2O would be lost by removal of OH from this carboxylic acid and H from this carboxylic acid, right? So another water molecule is formed. So this is now 2H2O. And now both these molecules will make bond with each other. So the oxygen will make bond with carbon, and this carbon will make bond with the oxygen. So two ester linkages have now formed. This is one ester linkage, and this is another ester linkage. And if you now solve the and if you now write the molecular formula of this compound, so it has 1, 2, 3, 4 carbons, C4, 2 plus 2, 4 hydrogens, H4, 1, 2, 3, 4 oxygen, C4, H4, O4. So this is exactly the same molecular formula they have given us. So the Y is a diester. Y is a diester, or we can say a cyclic ester, when two molecules which have both carboxylic acid and alcohol present in them, those two molecules can react with each other and they would form a cyclic ester, just like this one. Okay, so this is another question. A different trihalomethane CHCl3. This is basically from October-November 2018, paper 22. This is a part from question number 3. We are solving question number 3C. So a different trihalomethane reacts with oxygen to produce carbonyl dichloride. So we have some trihalomethane. Trihalomethane we have, that means we have three halogen groups. So this is CHCl3. So this is trichloromethane, reacts with oxygen to produce carbonyl dichloride. And this is the structure of carbonyl dichloride. This is carbonyl group. It has two Cl attached to it, so that's why we are calling it carbonyl dichloride. So HCl gas is also released as a product of this reaction. When trichloromethane reacts with oxygen, we get carbonyl dichloride and HCl. So write an equation for this reaction of trichloromethane with oxygen. So the reaction would be CHCl3 reacts with oxygen, we get carbonyl dichloride. Its molecular formula would be COCl2 plus HCl. So now let's balance the equation. So we have one carbon here, one hydrogen, 3 chlorine, 2 plus 1, so 3 chlorine, and we have only one oxygen on the product side. On the reactant side we have two oxygens. So to balance the oxygen, we would write 1/2 with this oxygen. So half molecule of oxygen, that means we have only one atom of oxygen. So now this equation is balanced. Now the next part is the conversion of trichloromethane to carbonyl dichloride can be monitored by infrared spectroscopy. The infrared spectrum of carbonyl dichloride is shown. So this is the infrared spectrum of carbonyl dichloride. On the infrared spectrum of carbonyl dichloride, identify with an X the absorption that would not be present in the infrared spectrum of CHCl3. So this is basically the infrared spectrum of carbonyl dichloride. This is carbonyl dichloride. And they're asking us to identify with an X the absorption that would not be present in the infrared spectrum of CHCl3. So let's first draw CHCl3. So this is CHCl3. So if you notice that in both carbonyl dichloride and CHCl3, we have carbon-chlorine bond here, carbon-chlorine bond here, and we have to tell the absorption that would not be present in infrared spectrum of CHCl3. So in CHCl3 there is no carbon-oxygen bond, carbon-oxygen double bond. But in carbonyl dichloride we have this carbon-oxygen double bond. So that means CHCl3, this would lack an absorption of C double bond O. Right, so first let me just identify it with an X. So which peak in this IR spectrum of carbonyl dichloride is representing the C double bond O peak? So this is 1500, 1600, and this peak here, this is around 1600. So if you look at the IR table, the carbon oxygen bond, let's say we have this C double bond O peak, this is in the range 1670 to 1740 ketones in aldehyde, right? 1670 to 1740. So we have this peak at around 1600, 1700, around at 1710 or 1720. So that means this is the peak X. So we would identify it with an X, right? And explain your answer. So what would be the explanation? The CHCl3 would have no C double bond O present, so no absorption at 1640 to 1620 to 1740, 1670 at 1670 to 1740. Suggest another difference between the infrared spectra of CHCl3 and carbonyl dichloride. So what other difference is there in between these two compounds? In the CHCl3 or in trichloromethane, we have a carbon-hydrogen bond, and there is no carbon-hydrogen bond present in carbonyl dichloride. So that means trichloromethane would have a peak at the CH peak is at, for alkanes, this is at 2850 to 2950. So we can say that the CHCl3 would have an absorption at 2850 to 2950, and COCl2 lacks it. So this is the other difference. Okay, so this next question is from October-November 2019, paper 21, question number 4. So we have this compound CH3,3-CCHO is used in the synthesis of some antibiotics. Give the name of this compound. And many students have problem writing the names of organic compounds. You just have to understand some basic rules, and then it is very simple, very easy, right? First, let's just draw the structure of this compound. They have given us the formula in condensed form. So first write this carbon. Whenever you have some groups present in bracket, then first write the carbon next to it. First just write the carbon next to it, and then we have 3 CH3. Bracket tells us that there are 3 CH3 groups attached to this carbon. Alright, so we will write 3 CH3, 1, 2 and 3. So this is the same thing as CH3, 3C. And then next to it we have CHO, that means C double bond O H. So this is an aldehyde. Now next you have to identify the longest chain of carbon atoms, and the aldehydic carbon must be present in it. So this is carbon number 1, carbon number 2 and carbon number 3. So the longest chain of carbon atom is of 3 carbons, and the carbons which are not present in the chain, those would be called the branches. So this is first branch and this is the second branch. A branch which has only 1 carbon atom is called methyl. So we have 2 methyl groups. The aldehydic carbon will always be carbon number 1. So this is carbon number 1, carbon number 2, carbon number 3. So the name of this compound would be, now we have 2 methyl groups on second carbon. So the rule is you have to give the position of all the branches which are present in the structure. It doesn't matter if they are present on the same carbon. So we have 2 branches present on carbon number 2. So we will give the position of both the branches 2, 2. This would be the position of both the branches. That means it has 2 branches attached to the second carbon. So 2, 2 dimethyl. Right? Between numbers you have to put a comma, and between the number and an alphabet there would be a hyphen. Right? So it is 2, 2 dimethyl. Dimethyl means 2 methyl groups are present on the same carbon, which is carbon number 2. 2, 2 dimethyl, and then we have 3 carbons, that means propane. Chain has 3 carbons, and because it is an aldehyde, so the names of aldehydes end with the suffix -al, propanol, and there is no need to tell the position of aldehydic group because aldehydic carbon will always be on carbon number 1. So this is 2, 2 dimethyl propanol. Next part is state the hybridization of the carbon atom labeled with an asterisk. So this is the carbon whose hybridization they want us to find out. So this is very simple. Finding out the hybridization of any atom, this is very simple. You just have to count 2 types of electron pairs. Just count 2 types. So whenever we have to find the hybridization of any atom, what you have to look for is the sigma electron pairs and lone pairs on that atom. Lone pairs are the atoms of the valence shell which are not taking part in the bonding. So we have to find the hybridization of this carbon, right? So we would count the total number of electron pairs, which included sigma electron pairs and lone pairs. So this is 1 sigma electron pair, this is second sigma electron pair, and then we have a double bond. In double bond means it has a sigma, double bond means it has a sigma and a pi bond. So pi bond would not be counted, right? We just have to count the sigma electron pairs. So that means this is the third sigma electron pair, and there are no lone pairs. No lone pairs present, only 3 sigma electron pairs. So whenever an atom has only 3 electron pairs, right, doesn't matter they are sigma or they are lone pairs, in total they if the total of the electron pairs are 3, if an atom has 3 electron pairs, so that means its hybridization would be sp2. This is some simple technique. If an atom has 4 electron pairs around it, sum of the sigma electron pairs and lone pairs are 4. Doesn't matter if all the 4 are sigma electron pairs or if 3 are sigma electron pair, 1 is lone pair, 2 sigma electron pair, 2 lone pairs. If the total of sigma electron pairs and lone pairs is 4, then the hybridization is sp3. If the total is 3, then hybridization is sp2. And if the total of the electron pairs is 2, then the hybridization is sp. So this is just simple formula of finding out the hybridization. For example, if they ask us the hybridization of this carbon, now if you calculate the electron pairs around this, first let me erase this thing. So now we have to calculate, or we have to count the electron pairs around this carbon. So 1, 2, 3, 4. Again, no lone pairs present here. Total 4 electron pairs. So 4 electron pairs mean this carbon is sp3 hybridized. So this carbon is sp3 and this carbon is sp2. And they have just asked us for the hybridization of this carbon, but I hope now everyone get this point, that how to find out the hybridization of any atom, right? Now, next part is 2 reaction sequences are shown. So there are 2 reaction sequences. This is reaction 1, then this is reaction 2, and this is reaction 3. Reaction 1 is an oxidation reaction. In reaction 1, you can see that we have some compound here, and this is reacting with atomic oxygen. Identify the reagent and condition for reaction 1. So for the reagent and condition, first we have to find out that which substance has been oxidized, which functional group is being oxidized. So in this compound, you can see that there is an aldehydic group present, and aldehydic group has been oxidized into acid, carboxylic acid. So whenever an aldehyde or alcohol or a ketone is oxidized, the reagent will always be acidified potassium dichromate. Conditions would be heat under reflux. Heat under reflux. Okay. Now the next part is A is this compound. A is a solid at room temperature. Now A is a carboxylic acid because it has COOH group present. And B is this compound, is an isomer of A. B is a liquid at room temperature. And if you look at B, it has this group present. So this is an ester, CO2, right? Carboxylic acids and esters, they are isomers of each other. So A is a carboxylic acid and B is an ester. A is solid at room temperature and B is liquid at room temperature. Explain the difference in the physical states of A and B. Explain the difference in the physical states of A and B with reference to any intermolecular forces that may exist. Okay, so we have to explain these difference in the physical states, that why, although they both are isomers of each other, then why A exists in solid phase at room temperature and why B exists in liquid phase at room temperature. So to explain this difference, you have to first find out, or you have just So to explain this difference, first you have to consider this thing that A is a carboxylic acid, and in carboxylic acids they have a stronger intermolecular force, that is hydrogen bonding, because it has this oxygen group present. So oxygen can make hydrogen bonds with other carboxylic acids. So let's suppose if we have this other carboxylic acid group present, it can make a hydrogen bond with this hydrogen due to the high difference of electronegativity. But B is an ester and it does not shows hydrogen bonding. So first of all, we would write that A, because we have to explain the difference with reference to any intermolecular forces. So A has hydrogen bonds between its molecules, and B has, so hydrogen bonding is the primary type of intermolecular force present in A, and B has permanent dipoles and temporary dipoles. Right? So hydrogen bonding is stronger than the permanent dipoles, and that's why it is solid at room temperature. So hydrogen bonding is stronger than permanent dipoles. So this is simple question. Now next, give the balanced equation for the reaction of this aldehyde with NaBH4 to form S. So again, this is the equation for the reduction of an aldehyde, right? So this is the reaction. You can see reaction 3. In reaction 3, we are reducing the aldehyde with the help of NaBH4. So whenever we write the equation for the reduction, first let's just calculate the empirical molecular formula of this aldehyde. 1, 2, 3, 4, 5. So we have 5 carbon atoms. 3, 4, 5, 6, 7, 8, 9, 10, H10O. So when we convert this, or when we reduce this aldehyde into alcohol, when aldehydes get reduced, they convert into alcohol. What would happen is that this carbon oxygen double bond would break into a single bond. Oxygen will gain hydrogen and carbon will also gain a hydrogen. So both oxygen and hydrogen will gain, both carbon and oxygen would gain a hydrogen. So that means this would be an addition of 2 hydrogen atoms. So the equation would be, okay, we will write the equation in this form. So it would be CH3 CHO. Now how many hydrogens have been added? 2 hydrogens. So this is hydrogen. 2 hydrogens have been added. So it would convert into, everything will remain same, CH3 3C, and now both the carbon and oxygen would gain 1 hydrogen each. So it would become CH2, and oxygen would gain a hydrogen as well. So this becomes, from CH it becomes CH2, and oxygen gains a hydrogen, it becomes OH. So this is the equation for the reduction of aldehyde into alcohol. All right, so the next part is draw the structure of the organic molecule T that reacts with A in reaction 2 to form U. So reaction 2 is this reaction. Compound A is converting into U, and we have to find out the structure of T that will react with A to form compound U. So if you look at these two structures, so compound U has this ester link present, right? And that means A is carboxylic acid, so that means T would be some alcohol. T is an alcohol that is reacting with A to form ester. So if I divide this ester into 2 parts, a simple way to identify the alcohol and carboxylic acid is divide your ester into 2 parts. Now this part, the part on the left, this belongs to carboxylic acid, the one which has C double bond O. This is the carboxylic acid part. So C double bond O, now this is carbon, it has 3, 1, 2 and 3 CH3. So that means this is the acidic part. So the other part would be the one which comes from alcohol. So this is alcohol, carbon number 1, carbon number 2 and carbon number 3. So that means our alcohol has 3 carbon atoms and OH group. Now this is the carbon which is directly attached to this alcohol. So that means the OH group is on second carbon. As you can see that the oxygen is connected to the second carbon. So that means this is propane 2-ol. So the structure of compound T is, either we can draw a skeletal formula. This is compound T, propane 2-ol. Alright, and the catalyst for reaction 2, the catalyst for esterification is sulfuric acid. Alright. Now the next part belongs to IR spectroscopy. X, Y and Z are all isomers of CH3,3CHO. So X, Y and Z are 3 compounds which are all isomers of this compound. A summary of some of the reactions and properties of X, Y and Z is shown in the table. So this table has 4 columns. Number 1 as compounds, then the observation with 2,4-D in pH, observation with Fehling solution, and the principal absorptions in IR spectrum. Okay, so number one, the first part is X and Y each contains a carbonyl group. So they have given us this information that both X and Y contains a carbonyl group. Complete the table with the expected observation for the reactions of X and Y with 2,4-D and pH. Now 2,4-D and pH is a test for carbonyl group. 2,4-D and pH is a test for carbonyl group, and as they have given us this information that both X and Y contains carbonyl group, so that means they both give orange PPT or red PPT with 2,4-D and pH. A confirmation with 2,4-D and pH is that we get orange precipitates, and same goes for Y. Identify the functional group present in Y that causes the recorded observation with Fehling solution. The functional group present in Y. Now X and Y, they both have carbonyl group. That means X and Y, they are either aldehyde or they are ketones. For the further confirmation that either we have an aldehyde or ketone, we react the carbonyl substance with either Fehling solution or with Tollens reagent. So Fehling solution will react with aldehyde but not with ketone. So X gives no reaction with Fehling solution. That means X is not an aldehyde, it is a ketone. And Y gives a red PPT with Fehling solution. So that means Y is an aldehyde, right? So the functional group of Y is aldehyde. Now Y has a chiral center and exists as a pair of optical isomers. Y has a chiral center and it exists as a pair of optical isomers. State what is meant by the term chiral center. So what is a chiral center? It is a carbon bonded to 4 different groups or 4 different atoms. So chiral center is a carbon which is bonded to 4 different groups. Alright, now the next part is draw the optical isomers of Y using the conventional 3-dimensional representation. So now we have to draw the optical isomers of Y. So for Y we have this information that Y is the isomer of this compound, and Y contains an aldehydic group and it is optically active. That means it has a chiral center. So the initial information about Y that we have is this, that it is the isomer of this compound CH3 3C CHO. Alright, now if I draw it like this, it has aldehyde but it has no chiral center because this carbon is connected to 3 other carbon atoms. So to draw an aldehyde with a chiral center, let's suppose if we have in total we have 3, 4, 5 carbon atoms. So 1, 2, 3, 4. Let's suppose if the chain of the carbon atoms is of 4 atoms and this is the aldehydic group. Now if the 5th carbon is attached to the 2nd carbon, because this is carbon number 1 and this is carbon number 2. So if I attach the CH3 group to this carbon, so now this is CH3, this is CH2 and it has this H attached. So you can count the carbon and hydrogens, these two structures, structure number 1 and 2, they are isomers of each other. And now if you look at the structure of this compound that we have drawn, it has this carbon which has 4 different groups. You can simply find it out that it has a hydrogen group attached on the bottom, then we have this aldehydic group and then a CH3 group and a CH2 CH3 group. So these are 4 different groups, so that means this carbon is chiral, right? So we have a chiral carbon and it has an aldehydic group present, plus it is the isomer of this compound. So this is the structure of Y. Now we have to draw the conventional three-dimensional representation. So to draw the three-dimensional representation of optical isomer, the simple way is to draw two bonds with the unbroken lines. That shows the bonds which are on the same plane, then a bond with a dotted line. This is below the plane. A bond with a dotted line means it is below the plane, and a bond with a wedge means it is above the plane, right? And then we have again the other isomer, that would be the non-superimposable mirror image. Now to draw the optical isomer or the non-superimposable mirror image, what you just have to do, just switch the left hand and the right hand side, right? So it would be like this. So this is the non-superimposable mirror image of the compound, and now we just have to attach the groups. So we can attach any groups, like let's suppose we have an aldehydic group at the top, and then this is C2H5, and we have a hydrogen present on this side and a CH3, right? So the arrangement can vary. It doesn't matter that in what order you have arranged these atoms around the chiral center, but whatever you have, whatever arrangement you have chosen in here, you have to follow it here as well. Just switch the left hand and right hand side. So this C2H5 would be shifted on this side, and H would be on this side, and CHO would remain in the top, and CH3 at the bottom. So these are the conventional three-dimensional representation of the optical isomers of Y. Next part is Z has a branched carbon chain. Z is another isomer of the compound. We have X, Y, and Z. So they're saying Z has this molecular formula C5H10O, and it has a branched carbon chain. It shows geometrical isomerism. That means it is an alkene, right? Complete the table with the bonds responsible for each of the principal absorptions seen in the IR spectrum of Z. So they have given us three IR absorptions, and we have to tell the bonds which are responsible for these absorptions. So the first one is 3200 to 3600. So 3200 to 3600, we have to move on to that table. Okay, so 3200 to 3600. Now this is the absorption range, 3200 to 3600, and the bond responsible is OH. And as the molecular formula suggests, the compound Z has oxygen present in it, so that means it could have an OH group present. So it would be OH group. Okay, so this would be an OH group. All right, and then the peak at 1630, for the absorption range at 1630, so that would be and 1050. So 1630 and 1050. 1630, obviously it could not be a carbonyl group because it doesn't have two oxygen atoms. And it has, they already told us this thing, that it has a geometrical, that it shows geometrical isomerism. So that means it could have carbon-carbon double bond, and the range also justifies 1500 to 1680. So that means at 1630 we get a carbon-carbon double bond absorption, and 1050 it would be CO bond, because if it has an OH group present, so the oxygen would also be attached to carbon as well. So this is 1040. So we have found out all the three absorptions, all the three bonds which are responsible. So 1630 for the absorption, principal absorption at 1630, carbon-carbon double bond, because the information tells us, the question tells us that it has, the compound shows geometrical isomerism. All right, and 1050, this would be due to carbon-oxygen bond. Now draw the skeletal formula of Z. Now Z shows geometrical isomerism. That means it would have carbon-carbon double bond. In total, it has 5 carbon atoms. right? So 5 carbon atoms, that means, let's suppose if it has 1 carbon on this side, CH3 and H, so these are 2 different groups attached to the double bond, CH3H. Now 2 more carbons we have to draw. So let's say if it has this hydrogen attached and CH2, CH2OH. Now if we count the atoms, carbon number 1, 2, 3, 4, 5. So this is C5, 3, 4, 5, 6, 7, 8, 9, 10, H10 and 1 oxygen. And it has a carbon-carbon double bond which shows geometrical isomerism because both the double bonded carbon atoms, they have 2 different groups. This carbon has an H and CH3 and this carbon has an H and this alcohol. So 2 different groups, and it has this oxygen hydrogen bond and carbon oxygen bond as well. So this is the structure of Z. Next part is X contains a carbonyl group. So they have given us 3 isomers, X, Y and Z. We have drawn the structure of Y, we have drawn the structure of Z. Now they're asking about compound X. So X contain a carbonyl group and X reacts with HCN. So if a compound has a carbonyl group, it can react with HCN in the presence of a small amount of sodium cyanide to form this compound, hydroxynitrile, as shown. Draw the mechanism of the reaction of X with HCN. And while drawing this mechanism, we have to draw the structure of X and the intermediate and include all charges, partial charges, lone pairs and curly arrows. And just remember this thing, that X contains a carbonyl group, but X was not reacting with the Fehling solution. So that means X is a ketone. X is not an aldehyde, X is a ketone. And the structure, it is the isomer of CH3, 3. So let's say we have this compound CH3, 3CCHO. X is the isomer of this compound. And if you see the final product, if you look at the final product of this nucleophilic addition of X with hydrogen cyanide, you can see that you just have to remember this thing, that whenever a compound undergoes nucleophilic addition, what happens is, this is a ketone. Now I'm just drawing a simple structure of a ketone. I'm not saying that it is X. We would replace these R groups with the carbon atoms afterwards. But first just remind yourself what is a nucleophilic addition. In nucleophilic addition, what happens is that cyanide group, let's say this is cyanide group with a lone pair and a negative charge, it attacks on partial positive carbon, right? It attacks on partial positive carbon, due to which this double bond breaks and the pi electron density move to this oxygen, right? And we get an intermediary structure which has carbon, O negative, R, and C triple bond N. All right, and then this O negative, this gains an H plus, which comes from HCN. This gains this H plus, and finally we get this kind of a structure. And now if you look at this structure, so this is the carbon, this is the carbon, this is the same carbon. It has OH group, this is OH group, and it has a cyanide group, so this is cyanide group. And now you can see that it has 2 alkyl chains, and both the alkyl chains are of 2 carbon atoms. So that means instead of these R, what we just have to draw here is C2H5. So we have found out the structure of X. So the structure of X is C2H5, and here also C2H5 and C2H5. So this is the simple way of identifying the structure, right? We just draw what the actual mechanism is, and then from the final product we found out the structure of X. Now state the role of sodium cyanide in the reaction. So this role of sodium cyanide is it acts as catalyst. Okay, so this is the end of the question.